Assalamualaikum and good day. In this video, I'm going to explain to you example A4 where we want to find the oscillation frequency at the system where the system at boundary condition or where the system is marginally stable. So given the diagram here, we can find the characteristic equation as given in the polynomial here. And then we can put in the polynomial into the Rath table. So we have this Rath table and we find the range of k. So in this example, I have explained in the previous video, we have the k range is from 0 to 6. Okay, and then what we can do is we can find the auxiliary equation. So how to find the auxiliary equation? We replace the value where we have the largest number of k. So in this case is 6 here. And then we replace it into the Rath table. So we replace k as equals to 6, 6, and then 6 over here. So what we have is we have at this position we have 6 minus 6 over 3 equals to 0. So we can take the row above that 0. So in this case, this at polynomial s square, we have this as our auxiliary equation. So when we put it into our polynomial, we have 3s square because the power of s square over here. And then remember that when we insert into the Rath table, we put it as an alternate number, right? So we have 132k. So in this case, we have our k is a power of 0. So we have actually k, which in this case we have replaced with the number with 6 that we have found in the earlier examples. We have equals to 0. So this is our auxiliary equation. And then we solve for the s. So we have s square equals to negative 6 over 3. And then we have s equals to square root of negative 2. And we can have this minus outside, we replace with j. And then we have these two. So it's actually s is equals to 1.41. Okay, so our frequency of oscillation where the system is at marginally stable actually is 1.41 radian per second. Okay, so when we put it onto the S-plane, actually we have at this position we have j omega, we have this sigma. So we know that when the system is at boundary stable or marginally stable, the poles are located on the j omega axis. So we have j omega d over here. So we have negative j omega d over here. The frequency of oscillation is actually given by this omega d. Okay, so the frequency omega d is the same because the poles are actually a complex conjugate. So what we can do is we find the value of frequency here using the auxiliary equation that I have explained earlier. Okay, so actually I can explain to you, or I demonstrate to you using the MATLAB, where we have in this example here, I can find the value of a frequency of oscillation using the seesaw tools. So I generate the seesaw tool plot, and what we have is we have this kind of plot, and then we change the value of k. In this example is c. We put it as 6 as we have found in the previous calculation. We know that when we put 6 into the c value, what we have is actually we have these poles that is located on the j omega axis, and you can see here this is undamped response where the value of zeta is equal to 0. It doesn't it neither decay nor decrease nor increase in this position. And you can see here at the bottom, the status bar over here, the frequency, the natural frequency, is given by 1.41 radian per second. So actually we have proven then when we calculate the value of S just now, and then what we have in the example using MATLAB, the value of a natural frequency is actually the same, 1.41 radian per second. So basically when you do your calculation, you can verify it using MATLAB. Alright, so I hope you understand my explanation on this example. If you have any comment or if you have any inquiries, please let me know and contact me in the lecture or using WhatsApp. Until then, see you in the next video. Bye bye.